Hello everyone! Various errors can occur when testing hypotheses. Understanding them and how to deal with them is the subject of this lesson. And hello again to this lesson, which essentially has two learning objectives. First, you should be able to explain what type 1 and type 2 errors are and how these are related to the significance level or the error probability. In addition, you should also know in this context what statistical power or just power is. This lesson is divided into 3 chapters. To get started, we briefly repeat the lesson's content on the concept and terminology of hypothesis tests. Type 1 and type 2 errors are explained using the analogy of a criminal trial. In the second chapter, the type 1 and type 2 errors are then explained using value distributions. The level of significance or error probability is also discussed. The last chapter explains the statistical power and what compromises must be made in hypothesis tests. Beyond reasonable doubt. Let's start with the concept of hypothesis testing using a criminal trial to explain type 1 and type 2 errors. As I said, this is just a quick recap of one of the other lessons. Feel free to jump to the next chapter if this is already known. In front of a court, hypotheses are put forward. Since the accused is assumed to be innocent, the assertion, "I'm innocent," is the null hypothesis. It is automatically assumed to be true. The prosecutor presents an alternative hypothesis, claiming the accused is guilty. To convince the judge or jury of the accused's guilt, the prosecutor must present strong enough evidence that an objective observer in the position of a judge or jury must reasonably conclude that the accused has almost certainly committed the crime. We consider 2 cases here. In the first case, on the left, we assume the accused is innocent. In the second case, we assume the accused is guilty. So, if the accused is innocent and the verdict is not guilty, then the prosecutor has failed to present sufficient evidence to convince the judge of the guilt. So, the prosecutor failed to reject the null hypothesis. The result is a correct verdict. But miscarriages of justice can happen. So, if the accused is innocent but wrongfully convicted, we call this a type 1 error. This is because a true null hypothesis was incorrectly rejected. If the defendant is indeed guilty and the verdict is guilty, then the null hypothesis has been correctly rejected and the correct verdict has been reached. But also in this case, a mistake can happen. If the defendant is guilty but wrongly acquitted, we speak of a type 2 error. The alternative hypothesis was wrongly rejected. This chapter explains type 1 and type 2 errors using probability distributions. When testing hypotheses, we first assume that the null hypothesis is true. Innocent until proven guilty was the basic assumption from the first chapter. The distribution of values is represented by an appropriate distribution. The significance level alpha then indicates the probability that a true null hypothesis will be rejected. A typical value for alpha is 5%. For example, if X is the quantity to be examined, it should be randomly distributed. For example, if this is an assembly's average breaking load, x bar, it is probably normally distributed. The test variable z0 can be calculated using x bar, the mean, and the population's standard deviation depending on the sample size. Z0 is then the so-called test statistic. So this test statistic is a number calculated from a statistical test. It shows how closely the observed data agrees with the expected distribution under the null hypothesis of this statistical test. In the first case, we assume again that the null hypothesis is true. Since the null and alternative hypotheses are mutually exclusive, the alternative hypothesis must be false. We said earlier that alpha is the maximum significance level we accept for rejecting a true null hypothesis. So, any value to the right of the critical value would cause us to reject the null hypothesis. If, as seen in this example, the test statistic Z0 is outside the critical region, then the null hypothesis is not rejected. So it is accepted. The result is not significant. The right decision. The same case again. The null hypothesis is true, and the alternative hypothesis is false. Only this time, the test statistic Z0 is in the critical region. The result is falsely significant. Although the null hypothesis is true and should not be rejected, it would be incorrectly rejected. This error is a type 1 error. Now we swap the truth content of the hypotheses. We know that the null hypothesis is false and the alternative hypothesis is true. If the test statistic is now in the critical region, like before, the result is significant and the null hypothesis is rejected. The correct decision. Alright, last case. The null hypothesis is still false and the alternative hypothesis is true. However, the test statistic is not in the critical region, but it should be. Since the result is not significant, the null hypothesis is incorrectly not rejected. We call this error a type 2 error. With the type 1 error, a true null hypothesis is falsely rejected. And with the type 2 error, a true alternative hypothesis is falsely rejected. This chapter will examine statistical power and its relation to type 2 errors. The parameters of the distribution of the null hypothesis are usually well known, since there is enough empirical data from history to calculate values such as mean and standard deviation. Only the parameters of the population are usually not known. To test the alternative hypothesis, one uses, for example, the data of one sample of size n. The test statistic, calculated from this data, such as the previously mentioned breaking load, randomly scatters around a mean value and forms its own distribution curve. This test variable can assume any value as it is randomly distributed. As a test statistic, we again take Z0, the value known from the previous chapter. This is the quantile of the normal distribution. Similar to what is known from the distribution of the null hypothesis for the significance level alpha, a similar value can also be defined for the distribution of a true alternative hypothesis. the significance level here is called beta instead of alpha. So if the alternative hypothesis is true, beta is the probability that the alternative hypothesis will be rejected. Thus, 1 minus beta is the probability that a true alternative hypothesis will be accepted. The probability of 1 minus beta is called statistical power. The statistical power thus indicates the probability of correctly detecting an existing effect and rejecting an incorrect null hypothesis. To clarify this further, the distributions of the null and true alternative hypotheses are shown one above the other. If the null hypothesis is true, the significance level alpha is the probability of getting a data point, here Z0, in the rejection region. So this is the probability of making a type 1 mistake, that is, falsely rejecting a true null hypothesis. 1 minus alpha is the probability of getting a data point in the acceptance region. This is the probability of a correct decision when there is no effect. But if the alternative hypothesis is true and an effect exists, 1 minus beta is the probability of detecting that effect. This probability is called statistical power. Power is a measure of a statistical test's sensitivity, the test's ability to detect differences. Beta is therefore the probability of falsely rejecting a true alternative hypothesis. So the probability of making a type 2 error. Finally, a few basic considerations on statistical significance and statistical power or test strength. Namely, the question of what role the effect size, the sample size, and the variance play. In the case of hypothesis tests, the size of the expected change, that is, the effect size, must be included in the considerations. And this applies to both the evaluation and the design of the test. The effect size, for example, is the difference between the mean of the null hypothesis and the mean if the alternative hypothesis is true. As can be seen here, this effect can sometimes be smaller or larger. If one compares the two wide areas, 1 minus beta, that is, the power, we can state that the larger the effect size, the greater the statistical power of the test. So the ability of the test to detect this effect. It's also logical. It's easier to find something big than something small. Another influencing variable is the sample size. A large sample provides more accurate values than a small sample. This means that with large samples, the mean of this sample deviates less from the mean of the population than with small samples. This leads to a smaller variance of the values, as can be seen clearly in comparing the two curves. Again, this has an impact on statistical power. With the same parameters, the area 1 minus beta is larger with a small variance, thus the power is again larger. So, the larger the sample size, the smaller the variance of the means, and the greater usually the power. The third factor to consider is variance as a trait in its own right. Because the variance of the sample also depends on the variance of the population, we can say that the greater the variance, the greater the risk of random sampling error, and thus the risk of detecting an effect that does not exist. What has just been discussed is also visible again in the formula for the sampling error or the standard error of the mean. The standard error measures how far the sample mean deviates from the true population mean. Without going into more detail about the mathematics here, I want to point out that we will frequently encounter the expression S or sigma divided by the square root of n when testing hypotheses, namely in the so-called test statistics. At this point, this is a reminder that standard deviation and sample size play an important role in hypothesis testing and significantly impact statistical power as the test's ability to detect an existing effect. So, that's a lot of information. Therefore, I will summarize the 4 most important key messages. A type 1 error occurs when the null hypothesis is true but rejected. The alternative hypothesis was, therefore, incorrectly accepted. A type 2 error occurs when the alternative hypothesis is true but rejected. The null hypothesis was therefore incorrectly accepted. Statistical power is a measure of the sensitivity of a statistical test, that is, the ability of the test to detect differences. And last but not least, when designing tests and interpreting the results, these 3 important factors must be considered: effect size, sample size, and variance. If you found this lesson helpful, please let me know and leave a comment. Thank you for that, take care and see you next time. Bye!